This is a segment about goodness of fit, but it's also perhaps a good time to review what I call a universal rule of thumb, or a metatheorem. This is something that most physical scientists learn in their training, and it's the idea that measurement precision improves as you get more data, and it improves as 1 over the square root of the amount of data that you have. Here, measurement precision, as used by a physical scientist, means what we might be calling accuracy of a fitted parameter in chi-square fitting or weighted least squares fitting. So here's a simple example of this metatheorem that you do probably already know. And that is the example where we're given a number of values x that are drawn from the same distribution. In fact, we're given n of them. And we want to compute the mean of those values. So here's the sample mean, 1 over n times the sum of the individual x values. Now what's the precision of this measurement of the mean? Well, let's take the variance of mu. And we can use the fact that the variance of constant times a quantity is 1 over that constant squared, here 1 over n squared, times the variance of that quantity. Now, variance is linear over the sum of independent random quantities. So we can take the variance of each of these, getting variance of x, and since we said that the x's were drawn from identical distributions, we multiply by n. Now notice that one of these n's cancels one of the n's down here, and the answer is that the variance of the mean is 1 over n times the variance of any single element in the mean. Or if we take the square roots of this equation, the square root of the variance of the mean, that is to say the standard deviation of the mean, is 1 over the square root of n times the standard deviation of an individual value x. But this phenomenon, the 1 over square root of n phenomenon, is much more general, and in fact it will go through on anything that resembles our chi-square fitting. So let's see how that works. Suppose I have some certain quantity of data, and I fit for the best fitting MLE parameters B0 here, and then I ask, how does chi-squared vary as I move away from that? Well, I'm at a minimum of a smooth function, so in general it varies locally parabolically like this. And the uncertainty of this B0 parameter is determined graphically here by taking a certain fixed offset delta chi squared and then seeing how much B0 can wiggle within that offset. Notice that the offset that I take here in delta chi squared is a number of order unity that doesn't depend on the size of the data set. If you recall, we had in a previous segment this table. I know it's now reduced to so small as to be difficult to read, but this table showed how much change in chi-squared you needed to include a certain fraction, probability 95% of the probability for the fitted parameters B0. Now I want to imagine that you have twice as much data. So what happens to this picture? Well, with twice as much data, because chi-squared is a sum over t values, t squared values, basically all the chi-squareds move up by on average a factor of 2. So if this is 0 down here, we move from here to here at the minimum. But we also move up by a factor of 2 at essentially any offset of the B0. So this new parabola up here has twice the curvature of our original parabola down here. And therefore, when we apply the same delta chi squared to get this blue line here, and then ask what is the wiggle room for the parameters, what is their uncertainty range, you can see that that will be smaller by a factor square root of 2. You can see that in the picture that this intercept, if I bring it down here, is a bit to the left of this intercept, if I bring it down to here. Well, now to goodness of fit. Up to now, we've always assumed that there's some value of the parameters b that make the model y as a function of the x's where we make the measurements and the parameters b, that for some value of b at least the model is correct. And now we have to ask what's going to happen if that's not true. Now assuming that some value of b's are correct is a very Bayesian thing to do, because Bayesians have to start out with an exhaustive and mutually exclusive set of hypotheses. A consequence of this, though, is it makes it very difficult for Bayesians to talk about the notion of a model's goodness of fit, because if a model doesn't fit well, it's an admission that you didn't have an EME set of hypotheses when you wrote down the model. So we're going to have to be frequentists for a while again here to make sense of this. So suppose that the model does fit the data, and that in fact will be our null hypothesis. Now our statistic is going to be just chi-squared. That is to say, for each of the n data points, we take the measured value minus the model value. We divide by the error of that measurement so that this becomes a t-value, and we square it. And of course, the chi-square statistic in the null hypothesis is the sum of n t-value squareds. So if we imagine repeated experiments, which of course Bayesians refuse to do, but frequentists do very naturally, under repeated experiments, the value of this statistic should be distributed as the sum of n t-squared values, and that we know is the chi-square distribution with an argument n in here. Now we're all set up to do a p-value test. In other words, if our experiment is very unlikely to be from this distribution, then we can consider the model as being disproved. So chi-squared is not just a way of fitting for the parameters, it's also a statistic that lets us decide by a p-value test whether the model fits at all. Let's try this on our example from previous segments, the 20 data points that fit to a falling exponential plus a Gaussian bulge in the middle. And if you go back and look, you'll see that when we did the fit for the best fitting 5 parameters in this vector b0, we actually got a chi-squared value of 11.13. Now there are 20 data points, so when we add together 20 t-squared values, we should get something that's distributed as chi-squared of 20. And it's actually a little odd that this value, 11.13, is fairly unlikely. It's in the left tail of chi-squared of 20, and it has a tail probability of only a little bit more than 5%. So we wouldn't exactly rule it out, but maybe that causes us to worry a little bit. In fact, we'd be right to worry, because if you did many repetitions of this procedure, in other words, I generated for you 1,000 of these data sets, each with 20 points, and you fit the curve separately for each of those, and plotted a histogram of the chi-square values evaluated at the best fitting parameter values b0 for each of those distributions, you'd actually find out experimentally that those chi-square values are not distributed as chi-squared 20 that we might naively think. They actually will end up distributed as chi-squared 15. So where did this 15 come from rather than 20? The magic word here is degrees of freedom. What goes into the argument of the chi-square is not the number of data points exactly. It's the number of data points minus the number of fitted parameters, and that's called the number of degrees of freedom. Let's see how that works. Why are the number of degrees of freedom not exactly equal to the number of data points? Okay, let's first consider a hypothetical situation where the data has a set of linear constraints. So the data consists of a bunch of t-values that are each obtained by taking a measured value y, subtracting from the model here. I've changed notation a little bit. I'm going to call the model value mu sub I for each I, and dividing by the standard deviation. And by hypothesis, these are drawn from the normal distribution, the zero mean and standard deviation 1. And as we've seen several times before, the probability of the vector of these t-values is the product of the probability of the individual t-values, and that is a Gaussian ball, a symmetric distribution e to the minus a half chi squared, where chi squared is just the sum of these t-values. Now what's a linear constraint? A linear constraint would be some external circumstance that causes the measured values of y not to be independent, but to satisfy some linear relation, here that the sum of the yi's times some coefficients, alpha I, is equal to some constant value. So what are the consequences of a linear constraint? Well, let's take this equation and take the expectation of it. So the expectation of C is the expectation of C, but that's just C again, so now I can equate these two. And the expectation of this thing, which is also going to therefore be equal, well, the expectation brackets come inside to each yi, and the expectation of each yi is, by hypothesis, we see it up here, mu I. So now back to this equation, take the yi here and solve up here for yi. You can see multiplying by sigma I, yi equals sigma I ti plus mu I, and I've put that right in here. Okay, now the sum of alpha I sigma I ti is repeated here, and the sum of alpha I times mu I, which is up here, is just C again. So maybe this is a long way around to prove something that I could have proved more directly, but you see I can cancel the C's on both sides of this equation, and I get the result that a linear constraint on the y's corresponds to a hyperplane through the origin in this t sub I space. I should have said up here an affine constraint on the yi's because I have some constant here. And what I see is that an affine constraint on the yi's corresponds to a linear constraint, a hyperplane through the origin in the t sub I space. Now why is that interesting to know? What we've learned is that an affine constraint on the measurements in the yi space is equivalent to a linear constraint, a cut through the origin in the space of the ti's. Now, the ti's is the space in which the chi-squared lives. In fact, the value of chi-squared is just the radius from the origin in this space. And if we constrain from a ball a sum of n ti squareds to a cut through the origin, which is in one less dimension, that would be the sum of n minus 1 ti squareds, or at least a rotation of such. But since it's a ball, the rotation in this space doesn't change anything. So thus we learn that each linear constraint on the measured data reduces the number of degrees of freedom, the argument of the chi-square function, by exactly 1. Now this solves a problem of constraints, but that wasn't the original problem we were interested in. We were interested originally in the question of what is the correct number of degrees of freedom when we fit for a certain number of parameters. So in that case, we don't have explicit constraints on the yi's, but what I want to show you is that in effect we do have implicit constraints. And the way to think about this is to imagine that in the space of the yi's, each y is wiggling around within its uncertainty range. So that's filling a little ball of uncertainty in the 20-dimensional, in our example, the 20-dimensional yi space. Now as the y's wiggle, the b, the maximum likelihood parameters, also wiggle. And there are just 5 of those. The B0, the maximum likelihood estimate, lives in a smaller dimensional space. Now we're interested in how chi-square varies, not for all possible B0s, but for the particular set of B0s that were the MLE best parameters of our data. So as the y's are wiggling around, we want to constrain the way they wiggle so as to hold B0 constant at its MLE estimated value. The implicit function theorem tells us that if you try to hold constant 5 values on the output of a function, and you have 20 wiggling values on the input of those function, then those 20 wiggling values must be constrained by 5 degrees of freedom. So the number of parameters, the approximate number of linear constraints locally on the yi's, is degrees of freedom, which is the number of data points, minus the number of fitted parameters. So let's review what we've learned here about weighted least squares fitting, or chi-squares fitting. You write down your model. It has parameters. You construct a chi-square function, which is a function of those parameters given the measured data and its measured uncertainties. You minimize the chi-square, and that gives you the maximum likelihood estimate of the parameters B. But you're not done. Those estimates for B don't mean anything unless you have some way of knowing how accurate they are. So we've seen in previous segments, you compute the covariances among the parameters, or equivalently, you can translate using the table here that translates from confidence intervals to delta chi-squareds. You can find the region away from the minimum value of chi-squared, this ellipse is in the B space, which contains 95%, say, of the probability of the covarying B values. Or, if you don't like confidence intervals, you'll just quote the covariance matrix of those B values. But you're still not done, because now we've learned you can actually decide whether the model was a good model in the first place. And to do that, you go back to your chi-squared value evaluated at its minimum, and you see whether, by a p-value test, that's a reasonable chi-square value to occur in the chi-square distribution with the correct number of degrees of freedom. And as always in p-value tests, if the p-value is too small, you can reject the null hypothesis and say that your model does not fit the data. Now I have one additional point to confuse you with. I say that because whenever I say don't confuse at the beginning of a slide, about half the people watching are immediately going to become confused. So what is it that I want you to be confused or not confused about? In that last step, when we did goodness of fit with new degrees of freedom, the value of chi-squared that we expected for a good fit was about the peak of the chi-square distribution, or the mean of the chi-square distribution, which is nu. And then the chi-square distribution has a width, in fact a standard deviation, of square root of 2 nu. So if the minimum value of chi-squared for our data turned out to be anywhere in this region of nu plus or minus the square root of 2 nu, we would have called that a good fit. Or rather, we would have not rejected it by p-value test as a bad fit. The key idea here is that chi-square min is a random variable, but it's a random variable over the population of different data sets that might have been. And that's, of course, a frequentist concept, and that's the concept that allows a p-value. But now go back a step when we were computing the confidence intervals or the covariance matrix of B. And then we decided how big a range B could vary within by starting at chi-square minimum, the same value we had up here, and letting chi-square grow as we vary b, but it could grow by only an amount of order unity. It was the entries in the table back there, the table that tabulated confidence intervals and delta chi-squareds. So the random variable implied in this equation is over the population of possible model parameters, b's, but for a single data set. This is a concept that's shared by Bayesians and frequentists. So there's an apparent paradox here. If it didn't even matter plus or minus the square root of 2 nu, and this could be a large number as the number of data points gets large, if square root of 2 nu was not significant up here, how can an order unity value be significant down here when we get around to deciding what the uncertainty of the b's is? Well, there's a simple answer to that. It's not a paradox. The answer is that once you have a particular data set, then there's no longer any uncertainty as to what chi-square minimum is. You've chosen a particular data set out of the population of different data sets, and it has some exact value of chi-square min. Then within that data set, a change of order unity from chi-square min corresponds to a significant change in the fitted parameters. So as the number of data points gets large, although this uncertainty increases, this one you keep the same at the values that were given in that table. Now let's see how this can actually work out as a scaling in n, the number of data points. At the very beginning of this segment, we remarked that chi-square increases linearly with the number of data points. Now we're a little bit more sophisticated. We know that it's the number of data points minus the number of fitted parameters. So as in that first slide, delta chi-squared indeed increases with the number of terms in the sum. But delta chi-squared, the change within the allowed fluctuations of b, therefore will be this. It will be n because the number of terms in the sum goes up. And then it'll be the allowed range of b squared. Why squared? Because it's quadratic. We're at the minimum of the chi-squared function. Now remember our universal rule of thumb at the beginning of this segment, and you'll see why we introduced it there. The universal rule of thumb says that delta b, the accuracy on the fitted parameter, is getting more accurate as n to the minus a half. So if you put n to the minus a half inside here and square it, it'll cancel that n, and you'll see that it all works out consistently. Delta chi squared can be constant.